Hello and welcome to today's lesson on the photoelectric effect, which is part of the particles and radiation topic in AQA A-Level Physics. So in today's lesson we're going to try and understand the basics of the photoelectric effect. So if we're successful and we learn in today's lesson, we should be able to understand what the photoelectric effect is, define the key terms of the photoelectric effect, and finally mathematically calculate values of the photoelectric effect, which falls into the following part of the AQA A-Level Physics specification. 3.2.2.1 The photoelectric effect. So, the emission spectra of black bodies first led to the particle nature of light and all electromagnetic radiation being discussed, so we needed some further conclusive experimental proof of the particle nature of light and all electromagnetic radiation. So we looked at the photoelectric effect. Now the photoelectric effect is the emissions of electrons from a metal surface when electromagnetic radiation is shined on it. Now the electrons are emitted off the surface as they're given energy by the electromagnetic radiation to overcome their attraction to the nucleus of the metal and become free. So the electromagnetic radiation has given the electrons energy, which has ionized the electrons, and they've left the surface of the metal. So what we say is we say that the electromagnetic radiation has given this electrons energy and the electrons have left the surface and produced something called photoelectricity. Now the minimum amount of energy needed to overcome the electron attraction to the nuclei in the metal is called the work function. Now it's important to note that we define the work function as the minimum energy needed to release an electron from the surface. Now this is important as electrons will all require different amounts of energy to overcome their attraction to the nucleus as they exist in different orbitals around the nucleus. Now the work function is unique to every element since they all possess different electrostatic attractions between their nuclei and the electrons. Now it's important to note that the photoelectric effect is the proof that electromagnetic radiation such as visible light must act like a particle. Now this is because observations from the photoelectric effect do not follow the theorized behavior from wave theory. Now according to wave theory, if in fact electromagnetic radiation was a wave, it's important to note that if this radiation gives the electrons enough energy to overcome the attraction to the nucleus and leave the atom, making them move off the surface of the metal, it means that the intensity of the wave would affect electron emission. However, this is not observed. The intensity of the radiation never affects how many electrons are emitted. So this allows us to conclude that in this instance electromagnetic radiation could not be a wave. Now another thing would be that according to wave theory there will be a delay between the absorption of the energy from a wave and the emission of the electron from the metal surface. This is not observed. Electrons are emitted instantaneously after the radiation is shined on the metal. Now this tells us that in fact electromagnetic radiation such as light, it can be considered not as a wave but as a stream of particles which we call photons. Now each photon has an energy of hf and therefore we can work out what's going on if we consider that each electron can only absorb one photon at a time. Now firstly this means the emission of electrons happens instantaneously as only one photon is needed to be absorbed by the electron, and it also means that the only factor which affects how much energy an electron can receive is the photon energy. So it tells us that photon energy, which is only dependent on the intensity, on the frequency of the light, will affect how many electrons are emitted. So this tells us that intensity is not a factor, because if the individual photons do not have enough energy to make the electrons overcome their attraction to the nucleus, nothing will be emitted. So it's important to know that the higher the frequency, the more energy per photon. Now it's interesting to note that the minimum frequency to overcome the work function is what we call the threshold frequency. Now any energy above the work function delivered by the photon goes to the kinetic energy of the emitted photoelectrons. So this means the frequency of the photon determines if electrons are emitted and the speed speed of the electrons once they have been emitted. So the higher the frequency of the photon, the greater the speed of the photoelectron. So this can be shown in the following animation. Here, the photons have energy above the work function due to having a frequency above the threshold frequency, and this causes photoelectricity, this idea of these electrons moving off the surface of the metal. Now in this animation, the photons shining on the metal surface have an energy below the work function due to having a frequency below the threshold frequency, so as a result there's no photoelectricity. Now it's important to note that when photoelectricity has occurred and the electrons are part of a circuit, current can be made to flow. Now as we mentioned before, the photoelectric effect is the emission of electrons from the surface of a metal when electromagnetic radiation is shined on it. It's experimental proof that light must be behaving as a particle and not as a wave, and we can understand the particle behaviour in the photoelectric effect by considering a person trapped down a well. So imagine our friend here, Daniel, is stuck down a well. Now this is what we call a potential well, a well of an energy, and in this example we'll assume Daniel has no energy of his own. Now the amount of energy needed to pull Daniel out of this potential well is 100 joules. So we need to give Daniel 100 joules to escape this potential well. So if Roman lowers a rope and pulls with 80 joules of energy, can he get out? No, he wouldn't be able to get out. He would tumble back down to the bottom, as we imagine our well is very smooth and he can't grip to the side. But if Matthew lowers a rope and pulls with 100 joules of energy, can he get out? Well, yes, he will be able to get out of the well, but he'd not be able to move after this event because he has no energy of his own. But finally, if Lucas lowers a rope and pulls with 150 joules of energy, could he get out? Yes, he'd be able to get out of the well, and the additional energy, this 50 joules, becomes his kinetic energy. So it's important to note that the factor determining the energy pulling him out is the person on the other end of the rope. Now, this energy is coming in discrete amounts or chunks, and there's no values in between, which is very similar to how light and electromagnetic radiation works. Now, like Daniel in a well, we can consider the electrons in a metal to be in a well, a potential well, and the energy required to escape the potential well is called the work function. Now, we call this a potential well because it's there due to the potential attraction of the electrons to the positive metal ions. So we can consider each electron in a potential well due to their attraction to the nucleus. So the potential well is caused by the electrostatic attraction between the nucleus and the electron. Now the attraction is dependent on the energy orbital the electron is in. It would be a maximum if it was at the closest orbital to the nucleus, the ground state, and it will be the minimum if it was the furthest orbital from the nucleus, the outer shell. So it's important to note that the energy needed to overcome this attraction is called the work function, and this is the minimum energy needed, so we assume the electron is in the outer shell or the highest orbital, or even delocalized from the nucleus itself. Now it's important to note that this value is given for each individual electron, so it's a small number and given in EV. Now the work function is unique for each element, so you can see here that sodium, aluminium, copper, iron, cesium, potassium, they all have different work functions. Now an electron can only absorb the energy of one photon at a time to escape the well. So we know that the energy of a photon is equal to hf, so therefore this shows us that the electromagnetic radiation comes in chunks of energy, the energy of photons. So electromagnetic radiation is not continuous, rather it is discrete. This means that photon intensity is not a factor when the photon does not have enough energy to overcome the work function, because if the work function is greater than hf, there's no electron emission. If work function equals hf, the electron is emitted from the surface of the metal, but it can't move any further afterwards. Okay, and we call the frequency which causes this to be called the threshold frequency, because the electron has passed the threshold of photo emission. Below the threshold frequency, intensity would not affect photo emission whatsoever. Now above the threshold frequency, the intensity can affect the photo emission, as each photon has the energy to overcome the work function, so that's an important idea. Now if hf is greater than work function, the electron will escape the surface of the metal. So the kinetic energy of the electron will be the energy from the photon once the work function is being subtracted. Now in this example we assume no energy is lost to the internal energy of the surroundings. So we can say that the photon energy is equal to work function plus the kinetic energy of the emitted electron. electron. So say for example we know that the photon has an energy of 10 eV and the work function is 8 eV, well then the kinetic energy of the emitted electron must be 2 eV. If the photon has an energy of 20 eV and there's a work function of 12 eV, well then the kinetic energy of the emitted electron must be 8 eV. So it shows that for an individual emission, only the frequency of the photon can overcome the work function. Changing the intensity cannot overcome the work function. The intensity can only become a factor once the photon has more energy than the work function, it's above the threshold frequency, since the work function has already been overcome. And like we said before, if light was a wave, in this case the electron will be constantly bombarded with energy until they escape. This means that the photon intensity would affect emission. This is not observed. How bright or dull the light source is does not affect photon emission. So light cannot act like a wave here. Photoelectricity is proof of the particle nature of light. So in this example, the photon energy is less than the minimum energy for the electrons to escape, so no electrons are emitted from the surface. The photons have a lower frequency than the threshold frequency, which we can observe as a red colour. The photons are below the threshold frequency. Now in this example, the photon energy is greater than the minimum required for the electrons to escape, the work function. So the photon electrons are produced with a range of kinetic energies up to a maximum value. So these photons have a higher frequency than the threshold frequency, which we can see as a violet colour. Now we gain a range of kinetic energies as the work function assumes all of the emitted electrons are in the outer shell. However, the photon energy is just large enough in this example to cause emission. So if this was the case, we would still get free electrons, we would still get photoelectrons, but with zero kinetic energy produced. So we can observe the photoelectric effect with the following animation. We can charge our rods in this case by charging them to put electrons on those particular leaves. We then shine UV light on the particular gold leaf that will cause the electrons to be emitted, and therefore it will cause those leaves to droop again. So what have we learned? The photoelectric effect is the emission of electrons from the surface of a metal due to the absorption of radiation. The photoelectric effect proves that light must behave as a particle called a photon, as only frequency of radiation affects whether electrons are emitted, and there's no delay in emissions of electrons after the radiation is shined on them. The frequency affects if electrons are emitted, because they are if the photons have more energy than the work function, and they will also affect the speed at which they are emitted. The intensity affects the amount of electrons emitted if the photon energy is above the work function. The work function is the minimum energy needed for an electron to be emitted due to the attraction between the electron and the positive nucleus. Now in our assumptions of the photoelectric effect, one electron absorbs one photon, electrons are found in the outer shell of the atom, and there's no energy dissipated in the energy transfer. So we can write this down mathematically. We know that the energy required to remove an electron, the work function, plus the kinetic energy of the ejected electron will equal the frequency, the energy of the photon. So we know that E equals HF equals work function plus the kinetic energy. Now the work function is considered a minimum as we assume the emitted electron comes from the outer shell. So this is telling us that we assume the work function is a minimum. So by that logic, we've got to assume that the kinetic energy, which is the value of the electron emitted, is a maximum value. This happens because the photon energy splits between the work function and the kinetic energy. So if we assume the work function is a minimum, we've got to assume the kinetic energy is a maximum. Now in reality, you gain a variation of energies as the electrons are different distances from the surface of the metal when they are emitted, so they're not all emitted as a maximum value. So let's summarize what we've looked at in today's lesson. We've looked at threshold frequency, we looked at the photon explanation of threshold frequency, we've looked at work function, and we've looked at the stopping potential, where the photoelectric equation is HF is equal to the work function plus the kinetic energy, where EK is the maximum kinetic energy of the photoelectrons. So if we've been successful and learnt in today's lesson, we should be able to understand what the photoelectric effect is, define the key terms of the photoelectric effect, and mathematically calculate values of the photoelectric effect. I hope you've enjoyed today's lesson on the photoelectric effect, which is part of the particles and radiation topic in AQA A-Level Physics. Thank you very much for listening to today's lesson, and have a lovely day.